Hello, welcome to video 47 in the lecture Advanced Mathematic Modeling. So in the last video, we were looking at random walks in 2D. We saw that a lot of the analysis of 1D random walks can be used, but we have to take out into account the directionality. And now by an analysis of things like mean increments, mean square deviations, and the distribution of turning angles, we can start to analyze a lot of the properties of movements of animals and also of humans. And so this gives rise to the field of movement ecology, and this there's a lot of interesting examples, and maybe we will do one or two in the exercises, but this would go too far away from the purposes of this lecture. So, but to just give you some ideas, interesting research topics here in the moment, for example, is in the migration ecology. So if you have birds which migrate over whole continents in half a year, so how possibly do they know to find their breeding area or their winter habitat? Yeah, and then the question is this distribution of turn angles or the flight directions, is this somehow influenced by external cues, by the sun, by stars, or the Earth's magnetic field? And then the question is, how can we then make models of the random walk of migrating animals, how they go from one part in the Earth to the other? Other interesting research questions, for example, is in foraging ecology. So animals, of course, also move around to find their food, their resources. And then there's questions like, what would be optimal distribution of turning angles or these increments in general to locate certain food items which are placed somewhere in the plane. Yeah? And again, we can do this random walk theory to study this. But for the purposes of this lecture, I want to go to another direction, and we want which is related again to this diffusive and super diffusive behavior. So now under normal circumstances, when we have this formula here, so you see that the mean square displacement is dominated by this term proportional to t, so which basically gives diffusion. And now the question is, do we have also in 2 dimensions random walks which are super diffusive, which deviate from this? And in 1D random walks, make some space, in 1D random walks, when we were analyzing this, and then we have seen super diffusion, so diffusion where the square root of the mean square displacement increases faster than t to power 1 over 2 in time. So the super diffusion can appear either when this second moment of the increments diverges, yeah? And then we don't have this term at all. And so this means the increments can be sometimes very large, for example from a power law distribution, and this were the Levy flights that we analyzed. So this term could diverge. So we have increments where the second moment doesn't exist, or this correlation function could decay as a function of time very slow with time. So there could be power law decay, and so we have long-range correlations. So there is a long-term memory about the direction of the movement. So these were the two main explanations how we could have super diffusion. And now we can look again here at our two-dimensional version of this. So also here there's now these two possibilities to have super diffusion. Either we could have here increments where the second moment diverges, and then we come back to Levy flights in 2 dimensions, or we could have movements where we have a long-term memory. And let's start first to look at these walks where this term has decays very slow in time. So we're interested in random walks in 2D which are long-range correlated. So this means the increments the vectorial increments EI are not independent and this means if we have this autocovariance function EI times EJ, yeah, and if the increments have the same length, you know that's the cosine of the turning angle, this then goes as a power law function of I minus j, so the time difference in absolute values, to some exponent gamma. And we have, if we have something like this, then we have a long-range correlated random walk. And now we can now see what possibly could lead to this. So now we can have again the cases that the increments can have different sizes. Yeah, but the more relevant idea is again that the increments have kind of the same step length, but we have this the cosine of the turning angles, that this decays as 1 over I minus j to some power gamma. And now the question, so like what would this mean? So I mean, this basically means, so we have memory and directionality. So we have step lengths which have always now the same length, but let's say we started with a step length in this direction. This would be E1, and then we make some random walk, whatever. But in every new step, the walker remembers the first direction. He knew I wanted to go in direction east, and there is a tendency to remember this even after a long time. So the scalar product of later EJ here with EI here has a tendency to be large. So even after long times, the walker tends to go in the same direction as it did before. So there is a tendency to continue this. So he will go and continue in the direction he was going before. But now this was the direction, the correlation from this arbitrary first increment. So when you look at this, so it could mean like we have a bias in the movement. But the same thing, like take now the second step. The second step was going upwards, and also from this E2 on, there is a tendency later to continue in the same direction. So basically this means if you make a very large, so like this were the first 10 steps, now we zoom this out for a very long time. So there is a tendency of the walker to go in some direction, and then later of course he will turn, because on average there is no preferred direction, but then there is a tendency to go in this direction, then here. So basically there is a persistence. So the movement is constructed of persistent time intervals, or time intervals of persistence movements, where the movement is more or less going in the same direction. So that's a movement where the walker is not turning around microscopic, erratic everywhere, but when the movement for some reason randomly decided to go in some direction, there is a tendency, even after a very long time, still to go in the same direction. Of course, it's hard to visualize this by eye, because if we want to do it by eye, then I always try to put in here some kind of certain intervals, but this would be a persistence or memory in a certain scale. But we learned the hallmark of this power laws is just the scale freeness. So basically for every arbitrary time interval there is a tendency to repeat the previous motion. Yeah? And so these are the long-range correlated walks where the walker has a memory where he was walking before. Now you could of course ask, is this possible in biology? Can an animal have such a long memory? But that's a very different thing. But this kind of long range correlations was observed also in movements of organisms. So, and that was the one possibility. The second possibility is that here the second moment diverges, which would mean the distribution of the step lengths has no second moment. Yeah? And we had this idea also in 1D motions, where we say we have the step lengths, they have an arbitrary direction. Here in 1D it was only plus or minus 1. Now in 2D this will be a vector of absolute value 1. This adder where the, exactly plus or minus 1. And the adders, the step lengths, and the step lengths were taken from a power law. And then we had a walk where the increments very often are very small, but sometimes we had very large jumps. So how does such a Levy flight now translate to 2 dimensions? So if we go to 2 dimension, so this would be, in general, it would be random walks where the second moment diverges. And the typical example for this are the Levy flights. And so in the Levy flight, then we say that the increments, the absolute value of the increments are taken from a power law distribution. So maybe we call this absolute values L, so the step length of one step, and then the distribution of this P of L goes to L to some exponent. Yeah, I don't know how did we call it alpha. L to minus alpha. And the direction would be random. So direction random and step length taken from a power law distribution. And this is then directly the analogy of Levy flights we had in 1 dimension. So how does such a Levy flight look like? So we know from a power law distribution, so if we start somewhere, so most step lengths then will be very small. So we have a very small step, and then we have random directions, so very small steps, so the walker goes around, and then occasionally we have a larger step. Then we have again many small steps, and then we could have a very large step, and then something like this. So that would be typical example of such a 2-dimensional Levy flight, where the walker is sometimes concentrated on a certain spot and then kind of suddenly decides to make this very large step. I mean, the events in the tail of the power law distribution. So we have this rare long jumps. And so this kind of Levy flights, I mean, they were developed by Levy to describe the movement of ants. So there's many biological examples. So we have from Levy, this was about flight of ants. And then there was, and there's other examples, like you have it in fish and spider monkeys. But maybe the famous example is from this Swaminathan et al. And this was about albatrosses. You know, albatrosses are the very large birds which can fly a lot in the ocean. And so then there was data about the motion of albatrosses. But at this time it was not the full trajectory of the albatrosses was not resolved. But what was known is always the time there was a logger, and when the albatross was touching the water, so the logger realized this, and so like you can then imagine the flight of the bird. So it touches the water, is sitting on the water, and then it goes in the air, makes a large movement, and then goes down again. And from the time intervals to the next touching of water, then one could make a distribution delta t, and we have p of delta t, and then distribution looked like a power law. And there was this Nature article that albatrosses, the movement of albatrosses follows a Levy flight, and so this suddenly triggered the search for Levy flights in all kinds of other animals, and then so Levy flights were found in many different, we had the ants, albatrosses, birds, so there were fish, spider monkeys, and interestingly also humans. Now you could be ask why should we be interested in the movement of humans, and where do we know from this? So like for example, when you look for the movement of humans, then nowadays we don't speak about so much about walking, but more maybe movement by car, by airplanes, by railroad. So we have a superposition of very different movement modes. Superposition of many movement modes. Airplanes, cars, and so on and so forth. And then a lot of movement of humans is just by moving to work, so like commuting behavior, movement to the next supermarket or school or the working place. Occasionally then you have a very long displacement where humans maybe move to a different continent for conference or holidays or so on, or because they really move to a new place. And so all these superpositions, all these movement modes are superimposed, give the average movement of a human. And nowadays we're in a time of when we have the mobile phones, where you can really track the movement of individuals. Now, why is this interesting? And that's maybe in this year of the corona pandemic, that's maybe very clear. So when you want to know how an infectious disease, for example, is transmitted from one place in the world to another, the disease can only be transmitted if a person who is infected by the disease is really moving somewhere. And so the infection rate of a disease really depends, and the spreading behavior of the disease is really tightly linked to the movement behavior of humans. And this is, you see now in the pandemic, when politicians try to stop the spread of the pandemic, they try to make restrictions in the movement, because if all infected people have to stay within a certain area, the disease cannot spread out of this. But already before Corona, there was a big interest in the movement of humans. But now the question is, so the question would be, on average, would the movement of humans, would it be described by such a Levy flight, which means that sometimes we make very long displacements? And here the analogy would be, that would be maybe a motor by airplane. So sometimes we make a big distance, and then we go to a car and make a lot of small movements, and then sometimes we make again a big displacement. So is maybe the movement of humans really given here by such a power law, or is this rather a super-diffusive movement? Or is the description of the movement of humans more in the kind of diffusive behavior, and the movement, the humans on average would move around like the pollen grain in the Brownian motion example? And and then there was a very cool work by Brockmann et al. These authors, they studied not the diffusion of people, but the diffusion of the movement of dollar bills. And basically, so what they were doing, there was this one website where people gave a stamp on a dollar note. So if we have here $1, so this was really the paper, the money, the note, and they put here a certain number by stamp, and in the US you're allowed to stamp your money. And there it said, if you find this code, go to a web page and put in this number here. And so when people found this dollar note someplace in the world, they went to the internet and said, today on April 2nd I found this dollar note in this place in the US. And then later on, some other person 2 years later found the same dollar note in a different place in the US. And so it was possible to reconstruct the displacements of these dollar notes between different parts in the US. And since the dollar notes can only be displaced by movement of people, so this gave an indirect hint about the movement of people. And so Brockmann et al., then they made a very cool analysis, and one part of the analysis, they looked at here the delta x, so this displacement that dollar notes were doing in a certain time interval, and they looked for the distribution of this, and they really could show this follows the power law. And how to detect power law in such distributions we have seen a lot. And so this really indicated that humans on average really follow a power law, so the movement of humans is super diffusive. There's a lot more to this story about the movements of people, and nowadays with the mobile phone data and so on, this is much better analysis. This opened a whole new research field to analyze the movement of humans, and that's interesting for all kinds of aspects, from infectious diseases to economy and so on and so forth. Yeah. Now, interestingly, coming back to these albatrosses, now some years later, interestingly, it was found that the original analysis of the albatross data was wrong. So it turned out that the albatrosses sometimes didn't settle to water, but settled to some other places which are not on water. And so, in fact, the albatross was sitting a long time on a stone, for example, but since the loggers didn't track this, so it was thought that the albatross make a very long displacement. So it turned out, the albatrosses in fact do not do the Levy-flight. But since, and that's now the interesting thing, so if you have a research paper which can inspire an idea, even if some ideas in the research paper turn out to be wrong in the end, and I mean, in fact, most of science after some time are validated at some point when theory evolves, this doesn't matter so much if the spirit or if the cool idea behind the paper was so true and inspired so many different other works. That's more important than, in some sense, than the result of this one paper in itself. And so this Viswanathan et al. Albatross paper, this really created, it gave birth to the whole research field of finding this long power law distributed random walks. Unfortunately, now this became a bit of a kind of religious issue nowadays. So now from time to time there's a new paper where people say, okay, here we find power law or Levy-flight movement in some animals, and now then there's scientists today who are totally opposite to this idea and try to really fight against any evidence of power laws. Other scientists, they really try to find these power laws everywhere, and then there's heated scientific debates. But I mean, in the end, it doesn't really matter so much if the displacement is really a precise power law, and the power law is the best fitting statistical curve to describe such a distribution. In the end, it just is important if the distribution is a long tail distribution which has a long tail, meaning you have a movement which looks like this, so kind of this long, rare long steps and many small steps. But of course you could have such a movement also with, for example, by superposition of two modes, and that's what some other biologist says. Maybe you just have two modes of movement, so you can say an animal can just be in the foraging mode. It makes small steps and tries to find all food items in a certain area, and then it's decided this area is cleared, and then the animal makes a long jump somewhere else and then starts again making a searching. So you would have the two scale motion, which by first glance would look like something like this Levy-flight. Yeah? But this, of course, now the question, if you have really a power law or such a two-scale thing, depends really on the analysis of the distribution. And we have seen this depends on the range, the width of the scaling regime, and so on and so forth. And sometimes it's not so easy to decide if a movement is a real power law or not. I see the video gets very long already, and can you give here some hints, some flavors of the whole idea, because like every piece what I'm telling here could be a whole video in itself, but time is running in this lecture, so I cannot go too much in detail. But one thing I still have to do, we have to distinguish these Levy flights from Levy walks, because they're sometimes confused. So now, what is a Levy walk? A Levy walk is something similar to a Levy flight. We have again a movement which looks here exactly as this one we had here before. We have movement, a random walk, which has this very long straight lines, a lot of very small straight lines, long straight lines. But the difference is now that these long segments are, the animal is not moving from one point to the next in one step, because like here this means the Levy-flight means the velocity of the animal is very small, because here this pieces, because he's doing every step in the same time distance. So here on average it's the velocity is very small, and then he makes a long step, but the long step is done in one time step. So here we have a very fast velocity, then slow velocity, one very fast velocity jump, and so on and so forth. That's not so realistic for many animal movements, and more realistic is the animal walk, the Levy walk, where you still have this long range straight lines, but still at every time step the animal can only do a certain distance. So it takes many steps to make such a long distance. Then he makes some steps randomly, and then many steps in one direction. So the difference is between the Levy-flight, where the long range steps can be done in one time step, whereas in the Levy walk the animal is walking with constant velocity, but it means here these are the persistent time steps. So the Levy walk is more in the idea here of a long range memory, where for a long time the animal can move in a straight line and then suddenly decides to turn a lot around, and then decides to go for a certain time in a persistent direction. Yeah? And now, so the walk is always set together of persistent steps on straight lines, and the lengths of the step lines are now distributed as a power law. But here we have a constant velocity, in contrast to the Levy-flight, where we have this jumps. So we have here the animal is really flying to a different thing, and here it's walking. And so the Levy walk really is a good model for this for long range correlation, where for a long time there is a persistence in the directionality. Yeah? And also these long range walks very often are seen in animal movements. And that's maybe all I wanted to say about all this movement behavior. So the idea is that we take really the spatial aspect from the random walk series to describe movements of animals and humans. And there's many examples where this really makes sense, where we can really fit data. And here with the Levy-flights you have to be careful with the Levy-flight or walk. And here in the exercises we will do some of the examples. For example, interesting, if you have no movement, for example, of bacteria, this resembles this kind of behavior a little bit. The bacteria a very long time can walk or cannot walk, the bacteria, they swim in a kind of persistent way, and suddenly they're tumbling, they're randomly oscillate around until they decide again for a new direction and make a straight line behavior, this run and tumble movement of bacteria. We will, for example, explore this in the exercises. Yeah, and also Levy-flights and Levy walks I think we will analyze in more detail in the exercises. For this now, thank you.